DDPM's formulation. So even the name, if you see, they are called denoising diffusion probabilistic models. The process, I mean, the word denoising here actually stands for decoding. Okay, so we'll see the encoding process is also referred to as the forward process or the encoding process. The decoding is also called the denoising process or the backward process or reverse process. We'll get to that. So the point that I wanted to make here is there is no encoding here. We only have the denoising part or the decoding part. Okay. Now, just to be consistent with the notations that are there in the literature, in all the existing literature, I will make a switch in the notation. So we have been using X to denote the data variable so far. Okay, and we have been using the alphabet Z or Z to denote the latent spaces. Now I'll slightly change the notation here. In all DDPM literature, the data variable is denoted by X naught. Okay. Now this is what we have been denoting by X with X so far. Okay. So now the latent space let me write down the notations. So latent space is typically denoted by x1, x2 up to x capital T. Okay. Please note that we have been using Z so far. So we were using Z1, Z2 up to ZT to denote the latent spaces. But now the literature everywhere, right? I mean, if you look at all the papers and other descriptions of tutorials of DDPM, you see this particular notation. So therefore, I will resort to this notation so that I just want to be consistent with the existing literature. Now, please note that this x1 to xt is not the same as the data samples that we have. So I will just erase this. Okay, just to disambiguate the notation. So given data d is equal to, well, say let's say that there is only a single data point x naught. Okay, now this is now being sampled from p of x naught because x naught is the underlying data distribution. Okay, x naught is the data distribution. So right, this is the data distribution. Okay, so please note the change in the notations. Yeah. So now whenever I use x1, x2, xt, so these are latent variables, and in all our treatment, just like with the case of VAEs, I'll assume that there is only a single data point x naught, and this can be trivially extended to the case where there are multiple data points just by putting a summation or an expectation with respect to all data points at the outside. Okay, so this is the idea. So we are assuming that there is only a single data point that we are given x naught, and this comes from the distribution p of x naught. The latent space is denoted by x1, capital X1, x2 up to x3. These are not the samples of the data distribution, but rather latent variables. Okay, so please note this important notational change in this course, and I'll do this only for the DDPM discussions because, as I said, this is consistent with everything that is published there. Okay, so I'll maybe write that. So not to be confused with previous notations. Previous notations where x1, x2 up to dot, these were data points. Okay. Now in a DDPM, these are the latent vectors corresponding to a given data point x naught. Okay, so in a in the DDPM literature, x naught denotes the data point, and x1, x2 up to xt denotes the latent space or latent vectors. Okay. So this is the change in the notation. Okay. Now let's write down the encoding procedure in a VAE, in a DDPM. Encoding, and it's also called the forward process. So it is called the forward process because we are starting from the data space and gradually projecting it onto several latent spaces. So now the notation is we start from x naught, okay, then we will go to x1, then we will go to x2, and so on, and we have x capital T. Okay, so this is the encoding process. Now this is the data point, this is the data point, and all of these are latent vectors corresponding to this data point. Okay, latent vectors corresponding to x naught. Okay, this will be our notation. So please note that, as we said, the dimensionality of every xt is equal to the dimensionality of x naught. Okay, for all t, and capital T typically is, which is how many number of latent spaces that one needs to consider, is a hyperparameter which is chosen experimentally. So we will discuss about this hyperparameter later. Okay, now I said that this is a latent variable model. The DDPM is a latent variable model, which means that let us now denote or define the model. So maybe before I define the model, let us complete the encoding process and then we'll go to the definition of the process. So I told you that the encoding process, which is now also called the forward process, I'll be using these terms encoding process and forward process interchangeably. Now the forward process or the encoding process, I told, is fixed, non-learnable, right? It's a fixed non-learnable procedure. Let us define the encoding process. Let's define the encoding or the forward process in a DDPM. Let us define the forward process in a DDPM. Okay. Now, what does the forward process do? It starts from the data space and then projects the data space onto the latent space. Okay. Now, what is done in a DDPM is that the forward process is defined as follows using these equations. So let's say that we have x naught, right? X naught is the input data point. Okay. Now this input data point is scaled with a scalar which is root of alpha 1, and it is shifted by a scaled version of a sample drawn from isotopic Gaussian distribution. Please recall that I told you that the forward process in a DDPM is fixed, but it is not deterministic, right? It is still a random process. Okay, so this is taken to be the first latent space. Okay, so now what is this? The first latent space is taken to be the scaled and shifted version of x naught, okay, which is the data variable. Now the scale is defined by a constant alpha 1, and the shift is defined by this some scaled version of a random sample that is drawn from a normal distribution. Okay, so this we will do iteratively. So now x2 will be root of alpha 2 times x1 plus root of 1 minus alpha 2 times some epsilon 2, where epsilon 2 is now drawn from again normal 0 1 and so on. So this is how we define it, and for a given x t, which is the tth latent space, just define that as alpha t times x t minus 1 plus root of 1 minus alpha t times epsilon t, where epsilon t is again a sample from normal 0 1. So now what are the unknowns here, where epsilon 1 to epsilon t, or let's call it as epsilon capital T, because we need capital T of them, okay, are fixed scalars, between 0 and 1, okay. Now this is called the variance schedule, and this is fixed to be a constant. This is again another hyperparameter, okay. Alpha 1 to alpha 3 t are fixed. Now diagrammatically, what does this signify? Let's say that we have x naught, which is an image, okay, that we start with. Let's say there is some house image that we have, okay, and this is my x naught. Now what is happening is the projection onto the next latent space can be looked into as, I just sample a Gaussian noise. This is my epsilon naught. This is root of, I scale it with alpha 1 minus alpha 1 again. So this adding with the noise will simply give me the first latent space, and this will be the data point with some noise added to it, okay. So of course we have the epsilon, you multiply this with alpha, so you multiply the data with root of alpha, and then take a noise, which is scaled Gaussian noise, and just add it to get x1. So this is the first latent space, okay. Now to get the second latent space, you take the image or the latent variable that you have. Note that all the latent variables are of the same dimension of that of the image. That's why you can interpret all of these as adding noise. So this will be root of alpha 2 times x2, 1 minus root of 1 minus alpha 2 times epsilon 2, where epsilon 2 is another sample, and we will get x3, which is the image with some more noise added. So we have some more noise added, and we keep going like this, okay, till a point where we reach x capital T, and it's not difficult to see that x capital T, hopefully with a large value on T, will be completely noise, where the image or the semantic content of the input data completely vanishes, okay. So this is how one can visualize what is happening. So now what is this? People who are already aware, one can see that this procedure, which is defining the forward process or the encoding process, please note that there is nothing to be learned here. There is no parameter that we are learning. This is a fixed process, okay, fixed encoding process. But here it's not deterministic, it is still probabilistic, okay. It's a random process because we are sampling from a Gaussian distribution at every time, but this is fixed, okay. So if one can see this, so this xt, this forward process that we have just defined, let me take the entire thing now. The forward process this is the above defines the encoding or the forward process of a DDPM. Okay, it's very easy to see that let's call this some equation 1. So equation 1 represents a first order Markov chain. It represents a first order Markov chain with Gaussian transitions, right? What is a Markov chain? A Markov chain is a random process, okay, which is a sequence of random variables where when you sample the sequence at every time, what you get is a random variable with an associated distribution. Okay, so a Markov chain or a Markov process is a special form of random process where, given that we have observed the t minus first random variable, the tth random variable is independent of everything else, okay, before that. So the first order Markov chain, let us define. So a first order Markov chain defines a series of random variables. Let's call them x0, x1 up to x capital T, okay, such that xt, okay, is independent of everything, you know, x t minus 2 up to x0 given xt minus 1. Okay, so if I know what my xt minus 1 is, then my xt is independent of everything, the entire past, given that I know the immediate previous random variable. So this is the definition of a first order Markov chain, and it's very easy to see or show that this expression, which is the encoding process or the forward process of a Markov chain or DDPM, represents a first order Markov chain. Okay, so this implies, what does this imply? This implies that one can define a series of conditional distributions. Okay, let me write that down. One can define a series of conditional distributions on the latent spaces, okay, latent variables, as follows. So now Q, let us define that as Q because it is the encoding process and we have been using the notation Q for the encoding process. So Q of xt given xt minus 1. So please note that Q of xt, the random variable at time t, only depends on t minus 1. Okay, the dependence is only on t minus 1, or the random variable at t minus 1 is independent of everything else. How do we define this? So we'll define that by the definition here. So if you look at this definition, then we have studied the reparameterization, right? I mean, a Gaussian variable can be reparameterized using any Gaussian distribution can be reparameterized using a Gaussian distribution with zero mean and unit variance. So it's very easy to see that because this is a Gaussian, this is a normal random variable distributed as zero mean and unit variance. If you scale it and shift it with something, xt will still have a Gaussian distribution with the mean and the variance defined by these two variables. So that we know. Okay. Now, therefore, this conditional distribution which defines the forward process can be defined as a Gaussian distribution on xt, because we are the xt is the random variable. Please note that we are talking about the forward process now in a DDPM is a first order Markov chain, and at every point t we get a random variable, because when you sample a Markov chain or a random process, you get a random variable at every time t. So the other way to look at it is that we are building hierarchical latent spaces at every time t. What we have is the tth latent representation of the given data point x naught. And from a diagrammatic point of view, so xt is the image or the data point that you get by adding the so-called noise for t number of steps. Okay, so this entire process can be looked into as this is like, so you take data, okay, plus add noise, let me write it as data, so add noise, and then we have the first latent space, right, which is noisy data, data plus noise. Noisy data, then again you add noise, okay, and then we get we'll say noisy data. I mean, just making this up. So, and you keep doing this. So now this is the first the data variable. You have the first latent space, you have the second latent space, and so on, and finally you only get noise only. Okay, this is the idea. Okay, this is x capital T. Okay, now these distributions are Gaussian distributions at the tth random variable. I was just saying that xt denotes the tth random variable in the Markov chain, or the tth latent space, or the data variable that you get after adding noise for t number of steps. Okay, this is at xt, and what is the mean of this? So the mean of this is given by root of alpha t times xt minus 1. Please note that when you condition a distribution, the condition random variable is always fixed at a given value. That is the definition of a conditional distribution, where the condition random variable is actually fixed to a particular value. Therefore, this is a constant, okay, when we are defining this. So this is the mean of this particular distribution, and the variance is given by 1 minus alpha t times the identity matrix. So why is this? This is because what we are actually doing here while defining xt is to take a random variable, a sample from the normal distribution with zero mean and unit variance, and then we are scaling it by some constant and shifting it with some constant. And if you take a random variable that is Gaussian with zero mean and unit variance, you scale it with some constant and shift it with some constant, we still get a Gaussian distributed random variable with the mean and the variance defined by the scale and the shift. That is exactly what it is. This is the reparameterization that we saw in the context of VAE as well, right? Okay, so this is the definition now. So this is the mean and this is the variance. Now please note that yeah, so I've already said that, right? The dimensionality of all this, these are all vector valued random variables. So therefore this is equal to, we are saying that this is all RD, right? This is all RD for all t. So we are talking about, I mean, if we are talking about images, all of the xt's have the exact same dimension as the initial data space, and the epsilons, or the so-called noise that we sample, also should have the same dimensionality as the data, of course, right? Otherwise you can't add two vectors. Okay, so this is the definition of the forward process in a DDPM. So this is because this thing, and q of xt given xt minus 1, this is called the conditional forward process. Conditional forward, or the encoding distributions. Okay, and there are t of them because at every t you can define a distribution this way. Okay, then what do we need? We have the fixed encoding distribution now, which is fully defined. Now we also need a decoding distribution, right? So let's define the model via a decoding distribution. Okay, so we all know what a model is, right? I mean, a model is a distribution over data p theta, right, which has a particular form defined by the latent variable, a distribution p theta. So let us define what the model distribution is in the case of a DDPM. So in a DDPM setup, so as we said, we have multiple hierarchical latent spaces. So we'll have to define a model that way. So we'll define that as p theta of x0, x1, x2 up to x capital T. This is equal to p theta of x capital T times the product of t equal to 1 to capital T p theta of x t minus 1 given x t, where p theta of x t minus 1 given x t is defined to be a Gaussian distribution on the t minus first random variable, and the mean is given as mu theta, the variance is taken to be some sigma theta. Okay. Okay. So this is the definition of the model. This is the definition of a model in a DDPM. Okay. Now here please note that this is actually nothing but the joint distribution between the data and the latent variables, because why is this? This is very similar to p theta of x comma z, right, which is the, in any latent variable model, let me write that down. P theta defines a latent variable model over the joint distribution. So p theta defines a latent variable model with multiple latent spaces. Multiple latent variables. Why is this? So it's very simple to see, because this is similar to a VAE, where what we define is that we define p theta of x comma z, right? So what is this? This is nothing but p theta of x comma z, because x0 is the data variable and x1 through xt is the entire latent variable. So this is the data variable and this entire thing is the multiple latent variables, right? So this is nothing but the joint distribution between the data variable and the latent variable. So this is the joint distribution between data and the latent variables. Okay, that's all. Okay, now unlike in a VAE, this has a particular form here, okay, which comes from the fact that the decoding distribution or the so-called model distribution is also assumed to be adhering a Markov chain, okay, in the reverse direction. So you have, here what we have done is, because we have represented time from left to right, from x naught to x capital T, in the decoding direction or the denoising direction or the reverse direction, what we need to do is start from x capital T and go all the way up to x naught. Okay, but because there are a series of random variables again, so one can define that as a random process, and that random process is also assumed to be a Markov process. Okay, it's also assumed to be a Markov process with Gaussian transitions, just like the forward process. But the catch here is that the mean and the variances of the conditional distributions at every transitions is learnable. Okay, so this definition of the joint distribution of the data and the latent variable arises because we are assuming that the reverse process is Gaussian. Okay, let me write that. Reverse process is Markovian. Now the definition of p theta definition of the model distribution p theta arises definition of the model distribution p theta in a DDPM arises because of the Markovian assumption, specifically first order Markovian assumption in the reverse direction. Okay, so this particular definition that we gave here, right, I mean, this is pretty simple. And if you take a Markov chain, okay, and want to write down the joint distribution of all the random variables involved in a Markov chain, a first order Markov chain, this is how it looks like. That's by definition. We've also made the assumption that the transition probabilities are also Gaussian, okay, with a mean mu theta and a variance sigma theta that are learnable. So now reverse direction with Gaussian transitions with learnable parameters. Gaussian transitions with Gaussian transitions containing learnable parameters. Okay. So now these distributions, okay, p theta of x t minus 1 given x t, they are called the conditional reverse processes. I mean, distributions that are there in the conditional reverse processes, right? We want to know these distributions. Okay, now mu theta, and actually we have to make this a function of xt as well, because mu theta changes at every xt. Mu theta of xt and sigma theta of xt are learned via elbow optimization. That's it. So now in a VIE, what did we do? We learned the encoding and the parameters of the encoding and the decoding distribution both. But here we only learn the parameters of the decoding distribution because our encoding distribution is fixed. Okay, so that is the idea. So now here this is the definition of the model for a DDPM, denoising diffusion probabilistic model, and we have made an assumption that the reverse process or the backward process or the decoding process is also a Markov chain with Gaussian transitions where the parameters are learnable. So I will actually make this a function of xt, easier to comprehend that way. So this is a function of xt and sigma theta is also a function of xt. Is also a function of xt. Okay, fine. So now we have all the model distributions or model definitions. There's one other thing that was not covered here is one can show that if one defines a Markov chain this way, as in the definition of the forward distribution, one can show that xt, the distribution of xt, right, which is q of xt, distribution of the final random variable can be shown to be equal to normal 0 1. So this is called the stationary distribution of the Markov chain. The Markov chain. So now if you have a first order Markov chain with this particular definition, one can show that the stationary distribution of that particular Markov chain happens to be a Gaussian distribution. Okay, so this is another known property that we will be using as we move on. Okay, so now the next thing that is to be done is that now we have to use all these definitions and use the standard elbow optimization to find these parameters mu theta xt and sigma theta xt for the reverse distribution or the decoding distribution. Okay, so let us look at that now. So what we need to do is elbow optimization to learn the decoding parameters. In a DDPM. So now please be a little patient with me because this might all seem a little abstract, but as we move on, a lot of clarity would emerge. So I'll also tell you how to, I mean, just like we discussed the implementation aspects of a VAE, and again, we'll also discuss the implementation aspects of DDPM. But so far, what we have seen is that a DDPM is a hierarchical VAE with fixed encoding or the forward process, where the decoding process is learned. So we assume that both the encoding and the decoding processes are defined by Markov chains with Gaussian transitions, while the encoding transitions or the encoding Markov chain that defines the encoding process or the forward process is completely defined. The decoding process is only defined up to the distributional level. So we know that they are all Gaussian transitions, but we don't know what their parameters are. So now what should we do is that given that we have data with us, we'll have to use these definitions, the model definitions and the usual elbow optimization that we have seen so far to obtain the decoding parameters. So that is the story so far. Okay, so what is elbow optimization? So please recall that in elbow optimization we start with the log of the likelihood. I am just going back to the previous notation here, and which was given by the marginal of this. So this we know is dc. This is the definition of a latent variable model, right? What we did was we constructed a lower bound on this, which we call as the evidence lower bound j theta of q phi in the case of a VAE, which was given by the expectation of log of p theta of x and z divided by q of z given x, and this was with respect to q of z given x. Okay, so in a VAE we made this q also a learnable distribution. Okay, this is what we have, but in a in a DDPM we have the exact same procedure, just that we have the elbow for DDPM has no dependence on the encoding parameters because it is fixed, right? This is the elbow for DDPM. This is equal to, we'll write the same thing, the expectation of log of p theta. What is this x and z here? In our notations, is it x0, x1, x2 up to x capital T, right? This is because we have t number of latent variables, divided by q of, again we have x1, x2 up to x capital T given x naught, because we have, this is z given x, right? And the expectation is with respect to the same thing, that we have q of x1, x2 up to x capital T given x naught, because x naught is the data variable here. Okay, I'll just write it in shorthand so that I can save some space. I'll write it as q of x1 to T given x naught. Okay, and this as log of expectation of p theta, we have x naught to capital T divided by, please note that while the model has a dependence on parameters theta, the encoding process here does not have any dependence. This is 1 to capital T given x naught. Okay, this is it. So this is the key equation that we are going to work with. So this is the elbow for DDPM is defined by this equation. Okay, now what should we do is that we'll have to use this definition of this evidence lower bound for DDPM and find a way to get these parameters theta of the model the way we have defined the model. That is what we are going to do next with a bit of algebra. I'll run through all this algebra quickly so that you appreciate what is happening, and finally we end up having a nice looking, very elegant equation to solve this DDPM, and I'll talk about how to implement that once we go through the algebra. So now the next goal is to use this evidence lower bound and the definitions of the models that we have seen so far and find the parameters of the model theta. So that is what we are going to do next.